guys, so by now you should hopefully have your full-size sheet of notes, your half sheet of examples, and you also make sure you have a calculator. So if you don't have those, go ahead and pause your video, go and grab them now. And you've hopefully had a chance to also look at your neighbors and the Google Classroom key for the homework assignment for 6.1 Part 1. So you can hopefully get any questions you may have addressed and turn it into the basket when you are done. Now, let's take a look at 6.1 Part 2. Well, we've already talked about mean, or the expected value. So the next logical thing is to talk about standard deviation of random variables, and these things called continuous random variables. So our essential question for today, how can I interpret the standard deviation of a random variable, and what is the difference between a DRV and a CRV? Okay, so as a reminder, please make sure that you hit pause and rewind as many times as you need to, right? You should have plenty of time to watch the video and get your examples completed. So, just to kind of lay the groundwork, we look at what type of measurement is E of x that we talked about last time. Was it center or spread? Well, this was a measurement of center, right? We said before that it was the mean, okay? The mean of any random variable. Now, what measurement of spread goes with the mean? Well, if you remember, we always paired together median and IQR, and we paired together the mean with standard deviation, okay? So, the next thing that we need to think about then is how do we calculate the standard deviation? Well, to calculate that, we need to first calculate this thing called the variance. We've talked about variance before, but only a little bit. It's going to continue to pop up, but in the next section, it's going to actually make more of an impact, okay? So the variance is sigma sub x squared. So really, here's the definition of what variance is. It's the average square deviation of all possible outcomes of the random variable x from its mean, or the expected value. It sounds like a mouthful. It sounds really confusing. To be honest, it kind of is, and we don't use it to kind of as an end. We don't use it in interpretation all that much. The value itself isn't even super important right now. It is kind of a road to get to the standard deviation, but it is going to come into play in a lot more significance later on. So we do at least need to remember what the variance is. So how do we go from sigma sub x squared to sigma x? Well, that should be pretty obvious, right? What happens when we take the square root of anything squared? We get the thing itself that's inside of it. So if we were to take the square root of that variance, we would get sigma sub x, the exact thing we're looking for. So how do we define it for a random variable? Good thing is it's not really different from what we have already learned about standard deviation. Standard deviation of a random variable is just how much a random variable will typically vary from the expected value, or the mean of that random variable. Interpreting it is actually really simple too. It's the same sentence starter that we had with one slight change. A randomly selected individual will typically vary from the mean by sigma sub x. So we change out the words individual with the context of the problem that we're looking at, and sigma sub x with the actual value. Okay, that's pretty much it. Now, let's go ahead and take a look at examples 1 and 2, and the nice thing is we're going to have to do very little by hand here. We're going to let the calculator do all the work, okay? If you remember, we never calculated standard deviation by hand. We used one variable statistics. So we're going to do the same thing, which means we have to go into a listen spreadsheet, and we are going to use two different columns here. One of those columns is going to be the random variable. The other column is going to be all the values for the probability of each of those respective values. Now, we have to make sure they line up. This is key, huge part. Each of those respective probabilities must line up with their respective values, okay? Then we go into our one variable statistics. Here's the thing that you have to pay attention to. The name of your random variable goes into your list, and then the probability goes into this thing called frequency list. This is the one big thing that changes right here, the frequency list, okay? So let's take a look at example number 1. Pull out your half sheet. I'll give you a moment to read this, and then we will take a look at what we need to do. Alright, so this prompt should look familiar, right? We looked at probability of certain outcomes, but we never calculated the expected value, and we definitely didn't do standard deviation for this one. So let's see how we can do it. If we were using the skills from last time, which are totally acceptable, we could find the expected value by that same formula we used last time. So, all together now, what was that formula that we used last time? For e of x, it was sigma pixie, right? We take each of the probabilities and multiply them with their values. So I have the value of one language comes up 63% of the time, two languages 29.5% of the time, all the way up to 5 languages, only 0.2% of the time. Okay, now I could do this by hand, but standard deviation then becomes a little bit tricky. Let's go ahead and do the one variable statistics and see what we get. Okay, so open up your calculators if you haven't already done so, and we want to make a new document. So we are going to open up our calculators and open up a new document. We want a listen spreadsheet. Now, up at the top, make sure you label this whatever our random variable is. Our random variable is languages, so I'm going to call it LANG, and the values I had for those were 1, 2, 3, 4, and 5, right? Go back up now to the probabilities, and I'll go ahead and name them PROB, okay? Short for probabilities. We go down to here, and we see one language had a probability of 0.630, two languages had a probability of 0.295, 3 languages with 0.065, 4 languages with 0.008, and 5 languages with 0.002. Okay? So, again, what we want to do here is do our one variable statistics, and we find that in menu. Then we go to option number 4. Option number 1 for stat calculations, and option number 1 again is one variable stats. Okay? The number of lists, even though we have 2 columns, we are only looking at one variable, right? And all of the values of our variable are in that LANG column. So we still have just one column, okay? The X list is our language. And then the frequency list, this is the thing that you want to change that's different. The frequency list shows, hey, how often do each of these values pop up? The value of 1 pops up 63% of the time. That's why we had to create the second one, okay? So what this does now is it takes into account all of those different things. If you did it by hand, you should have gotten 1.457 for your average. And here we see in our one variable statistics, we have X bar. We know that's the mean. Even though the notation's not right, we can still interpret it the same way. 1.457 is our average expected value for the languages. Now, what do we use for standard deviation? Well, there's S sub x, but that's undefined. So how do I tell the difference between S sub x and sigma x? We should remember that English letters are used for samples, sigma is used for population, but again, that doesn't even matter because, hey, this is undefined. So this is the only thing we can work with. And this happens to be the true standard deviation for the random variable, 0.67. So we write those things out. E of x is equal to 1.457, and sigma sub x is equal to 0.67, but we want to make sure we show where we got that, because this is all calculator work, right? We will say that's from one variable statistics. Okay? Now, the next thing we have to do is we have to actually type out our interpretation. Okay? So, typing out the interpretation, we just use those same sentence starters that we did before. If we randomly select many U.S. high school students, the average number of languages each student speaks will be 1.457. So that's interpreting the expected value, right? Now, how do we look at the standard deviation? We use that same sentence starter. Typically, a randomly selected student will vary by 0.45 languages spoken from the mean. And that's that. Okay? Not too big deal, right? It's all kind of the same stuff that we have used before, one variable statistics. Interpretations aren't really changing that much. Calculators doing all the hard work for us. So, go ahead and take a look at prompt number 2. okay? And we'll see what you guys get. All right, so we're going to move on to prompt number 2. Go ahead and hit the pause button to read through it, work it, and then you can check my answer. Yeah, I just said work it. All right, so here we're looking at a car dealership and the sales they make during a randomly selected Friday, just during that first hour of business. We've got our probability distribution. So we want to punch this all into our calculator. This, where you had your cars in one list, 0, 1, 2, 3, your probability here. Our one variable statistics shows us an E of X of 1.1, and we have the sigma sub X of 0.94. Okay, so let's take a look at how we interpret this value. E of X, 1.1, sigma X, 0.94. Remember, we want to say that's from one variable statistics. If we randomly examine many Fridays at this car dealership, the average number of cars sold during the first hour of business is just 1.1 cars. Now, typically, a randomly selected Friday will see sales vary by 0.94 cars from the mean in the first hour. That's the interpretation. And so what you think about this means there's actually a lot of variability, okay? A typical variation will see anywhere between 1.1 plus this 0.94 or all the way down to minus 0.94, which is essentially like selling anywhere between 0 and 2 cars would be seen as typical. Anything more than that would be considered atypical. All right, so the next thing we want to take a look at is the continuous random variable. So how is this different than a discrete random variable? Well, this is still a random variable just like we've seen before, but it has no gaps in between values. What it essentially is saying is that the variable takes on all values in an interval. We can't describe this using a table. We can't describe it using a histogram. We have to use a density curve. And so this is a nice chance for us to review some principles about density curves and see what does it mean for something to be continuous. I like this example using the same thing, describing the same thing. We can look at 2 different types of variables. Let's look at how big a foot might be. So imagine a shoe size, right? Shoe size could be 10, 10 and a half, 11 even. So those would be considered discrete random variables, right? What makes this discrete? Well, discrete means it can take on a specific value, but then there's a space or a gap between it and the next value, okay? There is something missing here. Now, you may have a size 10 shoe, your friend may have a size 10 and a half shoe, but I've never met anybody that has a 10.25 size shoe. Nobody I know has a 10.1 shoe, a 10.01 shoe, a 10.001 shoe, a 10.0001 shoe, right? There are clear, distinguished gaps in between all of the different possible values for discrete random variables. Now, a continuous random variable, on the other hand, might be something like foot length. If we were to take off shoes and start measuring things in terms of centimeters, I may find somebody that has a foot that's 20 centimeters, but maybe it's not exactly 20 centimeters, right? It might be 20.1 centimeters. But maybe I can be even more precise than that. Maybe it's just a little bit longer, and I have something else that goes down not to just the millimeter, but it goes down to the next level, 20.11 centimeters, or even further, 20.111, or 20.11111, or even 20.111100001. If I have precise enough instrumentation, I could go to as many decimal places as I want. And in theory, the distance between 20 centimeters and 20.2 centimeters is, yeah, we know it's only 0.2 centimeters, but there are infinitely many measurements I can take in between those two values, between 20 centimeters and 20.2 centimeters. Just depends on how precise my instrumentation is. So, again, a discrete random variable will have something with gaps, and a CRV, a continuous random variable, will be something that does not potentially have gaps in between its measurements. It can take any value in between 2 numbers. So another example of a discrete random variable might be like if you got a job, you're probably getting paid an hourly rate, right? An hourly wage. Maybe you work at a restaurant and you're making $10.25 an hour. Somebody else might have a really weird salary and it's $10.26 an hour. But Nobody is making $10.25. Nobody's making that. They don't do that. There's a clear gap between two possible salaries, right? Continuous random variable might be something more like time. Imagine you are an athlete and you're trying to measure your 40-yard dash time or your 100-meter dash time. We can, depending on how precise your stopwatch is, you can go to 1 decimal, 2, 3, 4, 5, 6, 7, a bunch of different decimal places, right? We could also do the same thing with weight. If we have precise enough measurements, we can go to as many decimal places as we want. Anything like that where you can continue to be even more precise, that would be considered a continuous random variable. Okay? So how do we work with CRVs? Go ahead and flip over your notes and we'll take a look at this XY axis that we've made here. Let's imagine a random number generator. It's going to select a random number between 0 and 1. Notice this isn't random integers, but this is random numbers, which means I could have a number like 0.1 or 0.2 or 0.3 or even 0.33333 repeating, right? Any number between 0 and 1. And we know that in theory there are infinitely many numbers between 0 and 1. Now, this has to be a density curve that we are describing here. Well, the only other thing that I remember about density curves is that the area underneath that density curve must be 1. So at most, the height of this can be 1, okay? Where we would have, thinking about the probability on the x-axis and the numbers chosen on the y-axis. Okay. So let's think about this for a second. Is the number 0.3 any more likely to be selected than the number 0.7? No, they are both equally likely. They have the same probability. Same probability as 0 being selected, same probability as 1 being selected. So what this means is this is actually a uniform distribution. You guys often want to call this like an equal distribution, but the technical term would be, the stats term would be uniform, where every single value has the exact same probability of being selected. Now, in this case, I want to know what's the probability that we randomly select a number between 0.3 and 0.7. Well, density curves tell us probability when we look at the area underneath that curve. What shape did we just shade in? A rectangle. The area underneath that rectangle is going to be the height times the width, right? Well, what's the width? From 0.3 to 0.7 is 0.4. What's the height? It's a rectangle. The highest point is 1. 1 times 0.4 is simply 0.4. So if you got your density curve, you can use some geometry understanding to be able to work with this and calculate probabilities of things that, so long as we can describe them with our density curves. The thing is, most of the time we don't work with uniform distributions like this. What we work with are, you guessed it, normal distributions. So, on the notes, this is a little bit of a change I want to make. I didn't type this out correctly. I don't want to think about this as imagining a probability distribution. I just want you to imagine a distribution that follows some kind of normal curve, like maybe weights of watermelons in a crop. Maybe they follow an approximately normal curve. So we can go ahead and draw out the normal curve with the mean right smack in the middle, and then we can mark out by the empirical rule the standard deviations, right? So we know there would be 20 there, and at one standard deviation we'd have 22, and at another we'd have 24, and another we'd have 26, right? And we can go the same way in the left-hand direction. That's all well and good, but again, this is like looking at the entire population. We're looking at random variables now. And so when we're looking at random variables, we have to think about not the entire population, but a whole bunch, an indefinite amount of randomly selected watermelons. Well, what turns out is that when we sample many, many watermelons at random from this crop, then that continuous random variable of a randomly selected watermelon is going to actually follow the exact same path as the population. It follows a normal curve with the same exact mean and the same exact standard deviations. And how can we find the area under any normal curve? Hey, we've done this before. It's z-scores, x minus mu over sigma. Only this time we aren't going to be using mu and sigma, the population standard deviation and the population standard deviation. We're going to be thinking about them as mu sub x and sigma sub x, right? That's what ends up happening. The expected value of the random variable, or the mean of the random variable, and the standard deviation of the random variable. So let's take a look at our examples. Again, turn to your half sheet and this first example. See that the weights of 3-year-old females are normally distributed with a mean of 30.7 pounds and a standard deviation of 3.6 pounds. So again, I'm going to mark my text. 30.7 is my mean, and standard deviation is 3.6 pounds. If I were to randomly choose one 3-year-old female and call her weight X, what is the probability that my randomly selected 3-year-old female is going to be greater than or equal to 30 pounds? Well, it says it follows a normal curve, right? A normal distribution. So go ahead and draw out your normal curve. This is like, there's almost no difference at all. In fact, when we were doing questions in chapter 2, we were really looking at continuous random variables and these distributions, right? So I draw my normal curve, mean of 30.7. 30 is off to the left of that. I draw my cutoff mark, but where do I want to look? Do I want to look to the right or to the left? We have at least, so we want to look at everything to the right of it, okay? So I can calculate z-scores, taking my observation, 30, a randomly selected individual, minus my mean of the random variable, 30.7, and divide it by 3.6. We punch that into the calculator, and we're going to get like negative 0.19, I believe. We can go to our z-table and find that value, but I want to show you how to use the calculator to do this too. We've done this with a few of you guys a few times, but never really practiced it too much. I want to give you the opportunity to do this too. Now you might be thinking, well, why didn't we always use the calculator? You need to be able to do it at home. You need to be able to use that z-table, and you need to just get that conceptual idea first before we get into the calculator. So let's turn on our calculators again. All right, so you can open up a Scratchpad and go into our menu. Now, since we're talking about probability of a randomly selected individual, we want to go to option number 5, probability, and we want to go into distributions this time. Okay, so in our distributions, we see this thing called normal PDF and CDF. Well, normal CDF is the option we can choose to look at the area in between two values. Okay, so we think about, we have to enter first our lower bound. Where did our cutoff start? It started at 30. So enter in 30 for your lower bound. Our upper bound, what's that number going to be? Okay, it really goes on and on and on forever here. We're shading in theory until infinity because this curve never touches the x-axis. Problem is we can't use infinity in the upper bound in our calculator. We have to have some finite number, so just some crazy big number, right? Just a whole bunch of 9s will do you. Now, the mean, we had the mean before of 30.7, and our standard deviation was 3.6. Click OK, and we have the area under our curve, 0.5771. We'll go ahead and round it to the 4th decimal place, okay? So, we can write that out. We have to show our work. Showing our work using the calculator command, we enter in what the command was, normal CDF, but we have to enter in exactly how we saw it or defining our what we call the parameters. So the first thing was 30, and we remember that that was our lower bound, right? Then we choose our upper bound. That's the next thing that shows up in our calculator. Then we use 30.7 for our mean. And our standard deviation was 3.6, and this gives us 0.5771. That's our area underneath our curve, and that is the probability of somebody weighing more than 30 pounds. That should make sense to us as well because this mark was to the left of the mean, which means it's more than 50%, but not by much, right? Now, whenever you are doing this normal CDF command, you have to make sure you use the lower bound, upper bound, mean, and standard deviation. You have to make sure that you define those parameters, okay? But I'm totally fine with you using it. So, go ahead and take a look at number 2. Make sure you draw your picture. Make sure you define your parameters, or you go through your z-score and z-table calculations. Okay, and you can check with me when you're done. Alright, so when you come back, hopefully you ended up with something like this. You've defined your parameters, your mean of 6.8, sigma 1.6, my lower bound, because we were looking at everything more than 9, and then my upper bound going to some really big number. We type in our normal CDF function into the calculator, and we should get 0.0846. So right now we have 0.0846. And that's it. We've now found the probability that somebody is greater than 9 scoring on this test. So how can you tell, a couple of things, how can you tell when to use the CRV normal distribution stuff? Well, anytime you see something that's going to follow a normal distribution, it's going to be a continuous random variable. If you see a probability table or a histogram, then you're going to want to use the sigma pixie calculations that we worked on last time. That's how you can, one way you can tell the difference between discrete random variables or continuous random variables. Okay? You're given a table, or you can make a table, discrete random variables, sigma pixie. It says it's a normal distribution, says it's continuous. We're going to have to do something else. Specifically, if it says normal distribution, we're going to be using z-scores or normal CDF calculations. All right? So that's that. Hopefully you guys enjoyed as much as you could. Have a wonderful day. Get started on your textbook assignment, and I will see you next week.